There's a battle going on outside, and this battle affects each and every one of us, and it reshapes the future. It is furious and it's raging, and I'm not talking about the Gaza or the Lebanon war. I'm talking about the battle over heterogeneous computing. Today, by the end of this presentation, you will know what are the benefits of heterogeneous systems, why do we need them, and how to program them, how to utilize the power that we have in heterogeneous systems. And we'll talk about the exciting news brought by C++26. A little bit about myself. My name is Oren. I'm a director of software engineering at Mobileye. I'm a computer engineering graduate from the Technion, also an MBA graduate from the Technion. I have 10 years of experience in hardware and software engineering at Qualcomm. And for the last 8 years, I've been working on acceleration, and I'm working on compilers. My enthusiasm is for compilers. I manage teams that develop LLVM-based compilers. It includes expert and talented engineers working on compilers. I'm also a former teaching assistant at the course of Theory of Compilation at the Technion. I'm also the organizer of the Israel LLVM meetup page. So if you're interested in compilers, LLVM, MLIR, I invite you to join our meetup page. So what are heterogeneous systems? Heterogeneous systems are systems that include various types of devices. It can be GPUs and other kind of DSPs. And in heterogeneous systems, you usually have a host, and this host can be like the main CPU, and you have multiple devices. You can have different types of devices, and you can have from each device several instances of this device. And the device can communicate between themselves, or maybe the host can be the one that sends transactions or tasks to the devices. And why do we need those devices? We need them because we want to accelerate. We want to be able to run our code as fast as possible. Think of Mobileye. Mobileye has needs to process an image. So let's take, for example, 1 minute, 1 second. In 1 second, we have to understand the environment. We need to understand if there is a vehicle, if there is a traffic light or traffic sign, if there is a pedestrian walking around. So we have 1 second to identify all of those objects in the image. And in order to do this, we need to be very fast. We need to have a dedicated hardware that can perform these calculations. And we need to do it much faster than 1 second. We're doing it many frames in 1 second. And we want to do it in power efficient way. We want to be energy efficient and to consume power as less as possible. And there are 3 pillars to perform acceleration in heterogeneous systems. There are other ways, but those are the main pillars to create acceleration. One is parallelism. You already talked about it in Iran lecture. Vectorization and locality. And I'm going to talk a little bit about each of them and how they map to the programming languages that we have in heterogeneous systems. So let's start with parallelism. In parallelism, you run your code on multiple compute units. You can execute a single or multiple instruction streams. For example, you may have a function that you want to offload to one of your devices, so you can just send it to one of the devices. Or you may have several, just one function that you want to parallelize it. It works on a huge data, and you want to parallelize it. Take part of the data to be executed on one device, and the other half to be executed on another device. And you can achieve it through data parallelism or task parallelism, and we'll talk about it more later. And it can usually be done by manually programming your code. For example, you can use one of the libraries that were talked about in the last session. And it enabled through asynchronous execution. So asynchronous execution is the key component for heterogeneous systems, because you want to be able to send your task to someone else, and then the main CPU can go drink coffee or do whatever it wants meanwhile, and to be able to create parallelism. The next thing is vectorization. If you look at this code, it does just a simple addition. It adds the array B with the array C and sum it up to array A. It looks pretty simple. And if I ask you how many iterations are done in this loop, so probably many will say that it's 1K. But the real answer is that it depends. It depends on your architecture, and it depends on your compiler. And why does it depend? Well, think of those arrays, and those types can be, for example, char, character. And this char is just 8-bit. And if my architecture is 64-bit architecture, I have a register of 64-bit, it looks like we have a waste of my register because I'm only using 8-bit out of it. So one of the ways is to vectorize my execution and squeeze 8 elements inside my register. So instead of performing a scalar execution, I'm doing a vector execution on 8 elements. So actually what I'm doing here, I'm not doing 1K iteration, I'm multiplying, I'm actually accelerating my code by a factor of 8. So I'm only doing here 128 iterations, which is much faster. It runs on a single compute unit, or it can run on multiple compute units. Usually you are doing it when you have multiple processing elements that can process each of the lanes in your vector. It executes a single instruction stream, meaning you have a single function and you just want to vectorize the loop in this function. You can also vectorize other things than a loop. But usually it is very convenient, very beneficial when you're working on a loop. And this is one type of a SIMD. You are running a single instruction, but you're doing it on multiple data. It could be automatically done by the compiler. The compiler, on contrary to parallelism, the compiler can perform this vectorization by itself. Not all compilers, but most of them can do it. And it depends on the architecture. The compilers know on which architecture you're going to run your code. So it compiles and it auto-vectorizes. You can also do it yourself. There are languages like OpenCL that has primitive types, vector primitive types that you can use in order to vectorize your code manually. So as I said, it is very useful for loops. And vectorization is a way for you to utilize your compute capabilities. The next thing is locality. If you have a CPU, and your CPU is really big and it has a lot of power, it's very heavy compute, intense, so you want to somehow drink through a straw the data that you need to consume from the memory. You need to read data from the memory and you need to write it back. But if this straw is really, really thin and you are not able to read the data in the rate that you need, then you are I/O bound, meaning that you don't have enough memory bandwidth. So you need to make sure that you have this memory bandwidth. So how do we do it? There are some architectures that enables to hide your memory latency through the execution. For example, let's take NVIDIA's GPUs. They have multiple threads in each of the GPU, and if a thread is now stalled because it is waiting for a retransaction, then in that case, it can continue to the other threads and return to that stalled thread once the transaction is finished. So this is one way to hide the latency. Caches may also lower the memory access cost, and the compiler can schedule transactions to reduce memory stalls. So if you have like a read transaction, and then you have a use of this transaction. And so what you can do, you can like reschedule your code, put your read on top as much as possible, and then by the time you'll get to the use, probably the data will be ready, or hopefully it will be ready. Okay? So by rescheduling your assembly code, you are able to hide the stalls. And there are some architectures that has local memory. Local memory, for example, scratchpad memory, that allows you to do fast iteration. The programmer has to control this local memory through like software managed cache. You can think about as a software managed cache. And in this local memory, you know exactly the performance that you want to get. So what are the types of heterogeneous devices? So we have, for example, GPUs. GPUs are very common. NVIDIA has GPUs. That's why NVIDIA is very popular. Cerebras has a huge wafer size GPU that includes also memory. It's very strong. There are digital signal processors. For example, Xilinx has a FPGA-based, it's a hardware-based acceleration based on FPGA. And TI, Texas Instruments, also have their own DSPs. There are many other companies. Those are just examples of companies that has types of heterogeneous devices. Neural processing units. Google has their own TPU, which is a tensor processing unit, there for accelerating deep learning and neural networks and machine learning. IBM has their own NPU as well. And there are other accelerated processing units. For example, Samsung has the HBM, which is a technology that allows you to do operations in memory. For example, instead of reading data from the memory to the CPU, perform some operation, and then write it back to the memory, you can do those operations already when they reside in the memory. So it saves you a lot of traffic. And also we have the EyeQ chip by Mobileye. Mobileye is not just an algorithm company. It includes also a software and a hardware. And on top of this hardware, we have a SDK, a full software development kit that enables us to execute fast and to accelerate. And Mobileye has all those kind of devices. And I'm going to show you now a short video by our CTO presented in the last AI Day at Mobileye. And in this presentation, he's talking about the trade-off between having like just a big CPU that does everything compared to a software, a hardware that is really, really dedicated for specific computation, specific tasks. And then he's going to show the portfolio of the devices that we have in Mobileye. And some of them will look very familiar for you because they are common in a lot of heterogeneous systems. Vectorization and data parallelism, all of those things are really common in many cases. So now we're going to talk about the chip, what's in the chip of the EyeQ.
A chip, there is an inherent trade-off between the flexibility of computing things for the chip and the efficiency of the chip. If you want a very, very flexible chip, take a CPU. It's Turing complete. It's the most flexible approach, but it will not be very efficient. Because it needs to do so many different things, it cannot be very efficient. On the other hand, if you need to do just a single operation, you can design a chip or a circuit that will do only this fixed function. It will be super efficient because you know exactly what you need to do, but it will only know how to do this particular function. So we have an inherent trade-off when designing a chip. GPU is somewhere in between. What the EyeQ6 family, and in particular I'm talking here about the EyeQ6 High chip, is we have 5 distinct architectures on this trade-off between flexibility and efficiency. On the one hand, on the left-hand side, we have an XNN. An XNN is something that is very, very, very specific for deep learning and super efficient. Since we know that we are going to do a lot of deep learning, we know that we want something that will solve deep learning, okay? Very, very good. But we are not doing just deep learning. We're doing more things, so we need additional components. So on the other spectrum, we have the MIPS. The MIPS is a regular CPU, okay? That is very, very flexible, but not very efficient. In between, we have additional PMA, VMP, and MPC components, which are accelerators that each one of them excels at something specific and moves us in this trade-off between efficiency and flexibility. So let's go from the most flexible to the less flexible and explain what are these different accelerators are doing. So as I said, MIPS is a general purpose CPU. The next one is called MPC. MPC is, again, very similar to MIPS. It's a CPU. You can think about it as a CPU which is really, really good at multi-threaded programming, multi-thread parallelism, okay? Because, so if you want to use it for a single thread, it will be less efficient than MIPS. But if you are doing something which is several threads, then it's more efficient than MIPS. This is how we design. Designed to excel at multi-threaded. You can imagine that, multi-threaded is something that you find everywhere when you build a software stack. The next one is VMP. VMP comes from the family which is known in the industry as VLIW and SIMD. VLIW is very long instruction widths, and SIMD is single instruction multiple data. We use it, for example, for the pre-processing of the images themselves. So think that we have many images, each one 8 megapixel, and we get, for each pixel, we get 12 bit of information. This is a huge amount of data, and you need to process it. What do we mean by process it? So for example, some task is tone mapping. You want, if you have the sun and you have a vehicle that is very close to the sun in the image, you don't want the vehicle to be washed out because of the sun. So you want to adjust the image so that the intensity will be adjustable according to the scene. This is called tone map. So this is a type of operation in which the bottleneck is dealing with a huge amount of data and you want to do it in parallel. So what VMP, in a sense, is doing is a machine being able to do operations on vectors. So you take a vector, maybe another vector, you can do an operation between them, and all of this operation on the big vector is done in a single cycle of the CPU. Okay? So this is what VMP is doing. PMA can do the same. So why do we need VMP and PMA? Good question. So VMP is very, very efficient, more efficient than PMA when working with integers, with fixed size numbers. PMA can handle also floating point numbers. So it is more flexible on the trade-off because it can handle floating point numbers, but it comes with a price. Per silicon area, VMP will be more efficient than PMA. So again, you want some of VMP, some of PMA, depending on the load that you are going to use in the chip. Finally, XNN is a very, very strong accelerator for deep learning. It basically knows to do only convolutions, matrix multiplications, and some activation. So very, very limited, but if you think about deep learning, then convolutional neural networks, check. Fully connected networks, check. Transformers, check, because what are transformers? It's just matrix multiplication and activations. So XNN is very, very efficient for doing the most heavy lifting that we need in order to run AI for deep learning. So this is how we get a great efficiency. Now,
okay, so for each of those accelerators, we need somehow to have a tool chain. We need a software development kit. So we need to develop compilers, and that's exactly what my teams are doing. They are experts in developing compilers based on LLVM. And we also need a runtime library to execute, to send those transactions and schedule them on the devices. So the real battle here is how to program those heterogeneous systems. Which programming language should we use? So here are some examples of heterogeneous programming languages. I'm going to talk about a few of them. So the first one is OpenMP and OpenAC. OpenMP and OpenAC are started as a pragma-based programming languages. All of those programming languages are based also on C++ or has extensions to C++. And OpenMP now supports many more. Then we have MPI, which is a message passing interface. Some of OpenMP was developed on top of MPI. CUDA, which is very popular, it is there, especially was developed for the GPUs in NVIDIA. And then we have OpenCL. Because CUDA is a little bit, it's not fully open sourced, so the industry decided that they want to create a standard, an open source standard. So many companies, hardware companies like Samsung and Intel and AMD and NVIDIA and ARM and Texas Instruments and other companies created this organization called Kronos. And Kronos created the Open Compute Language specification. So this is a standard that is there for all kinds of devices, not just GPUs, but many kinds of devices. But then we saw that it creates a lot of boilerplate code, and the adoption wasn't that good. So Kronos created a new specification called SYCL. And today I'm going to talk about 3 languages. I'm going to talk about CUDA, OpenCL, and SYCL. We are going to judge which one is better. It might depend on your needs, so you'll be part of the judgment who will win this battle. And I'm going also to talk a little bit about OpenMP, just to give you a small taste, and how all of this connected to C++. So first we need to have a foundation. We need to set the terminology. So kernels, as you probably know, those are functions that you want to offload to your device. Usually they contain a loop that works on a lot of data. You want to execute it on your device and to have task parallelism and data parallelism. In OpenCL, you precede your function with the keyword kernel to specify that this function is actually a kernel and you want to offload it to your device. In CUDA, you precede it with the keyword global. That means that you want this code to be compiled for your device. And in SYCL, you don't have to put any keyword because you infer it from the code itself. You understand which part should be executed on which device, and so you compile it to that device from your code. You actually can add such a notation, but you don't have to. Next thing is data parallelism. Imagine a big image, a 2D array contains a lot of data. And you have a local memory, and this local memory is really, really small. And you can't put all of this image inside your local memory. So you somehow need to split it, to divide it to tiles. And every time you just take one tile, copy it into your device, your local memory, do the operation, and just write it back to the memory. Okay? And now you want to create data parallelism, meaning that you'll have several devices, and one device will work on this tile, and this device will work on the other tile, and this device will work on another tile, devices or compute unit or whatever. So that's how you get data parallelism. You let each core or compute unit to work on a separate element, different element from the same array. The array can be one-dimensional, two-dimensional, or three-dimensional, and in OpenCL it is called ND-range, n-dimensional range. So the iteration space can be divided to workgroups. Each tile, we call them a workgroup, and a workgroup has a unique identifier inside your grid or your ND range. And each workgroup can be subdivided to work items. And each work item has its own unique identifier. There's a unique identifier inside your whole global grid or inside your workgroup. So the total ND range defines the number of work items that you have. You can think of a pixel as a work item, and you want each compute unit or each processing element to work on a different pixel from your ND range. So just to compare the terminology, both CUDA and SYCL, both are and OpenCL are talking about the same type of components but had different names. A work item in OpenCL is called CUDA. It's called thread in CUDA. Open OpenCL workgroup is called block in CUDA, and the end range in OpenCL is called grid in CUDA. The next thing is locality. We talked about locality before, and we said how important it is to have your data close to your device. It may reduce some memory bandwidth. It can help you to accelerate your code and to schedule it better. So in heterogeneous systems, you need to have a device memory model. So you have the global memory, which is like the big memory. It's a huge memory, and it's usually the slowest one. And it is used to transfer data between your host and the device. Next in the hierarchy, under the device, you have the compute units. You may have several compute units in your device. You can have one or more compute units, and the compute units execute workgroups. And each compute unit has its own local memory. The local memory is accessible by all the work items that are running inside a workgroup. And inside your compute unit, you also subdivide it to processing elements. And each processing elements, and inside the processing elements, you execute the work items. Each processing element has its own private memory. So basically, private memory is unique to every work item. So you have a compute device, and then you have compute units, several compute units inside your device. And inside compute units, you have what we call processing elements. But in memory-oriented, when looking on memory, we have the global memory, which is usually the slowest, the local memory that can be faster, and then we have the private memory. When comparing the terminology between CUDA and OpenCL, so OpenCL private memory is referred as sometimes as registers in CUDA. The local memory in OpenCL is referred as shared memory in CUDA. And the global or constant memory or shared is the same terminology in CUDA and in OpenCL. So now I'm going to show you code snippets. I'm going to show you the same program that just does add +5. In all those programming languages, or 3 programming languages that we talked about, and you will be the one to judge and see which one is better. Okay, so let's start. Okay, so first we are going to go over CUDA code. In CUDA, you can see that the program is not that big, is relatively small compared to what you'll see next in OpenCL. Let's look at the device code. The device code is just an add function. It is preceded with the keyword global. And I'm passing as an argument an array, a pointer, to a type called char4. Char4 is 4 elements of char. It's a vector type. In CUDA, compared to other languages like OpenCL, it's not exactly a primitive type, but you can implement the operations on those types. So I'm going to manually vectorize my code. I'm going to pass a char4. And inside the kernel, I have implicit arguments. You can see that I have here thread index and block dimension and block index. All of those implicit variables allows me to identify where inside my grid I am. Because I don't need to execute on all of my array. I just need to execute on my part, on my work item. In this case, I'm just doing a one-dimensional array. So I'm just using the x and not the y and z arguments. So I'm doing a head. This add is on a vector of 5, and that's all. That's all I'm doing in this function. Now let's look at the host code. The host code is responsible to execute, to offload your code into the device. We are running on the main stream. In CUDA, you have streams of execution. And so first, we are allocating memory in our device. We are going to copy the data from the host. Let's assume that we initialize the host pointer. So we're going to copy the data from the host pointer to the device pointer. And after that, we're going to execute our code. We are calling the add function, the add kernel, actually. And we are using a kernel launch operator, which is like 3-diamond operator. And inside this operator, we are specifying what is the end range that we want to use. We are specifying how many blocks and how many threads are there. And then we are passing the argument for this kernel. I don't know exactly when this kernel will be executed. It will be executed asynchronously. And after that, in the same default stream, I'm going to copy back data from the device to my host. And then I'm going to wait for the data to be ready for all the stream to finish. So I'm going to synchronize. By the end of this synchronize function, I know that I finished the execution. So this is a CUDA code. It's relatively small. And now I'm going to show you OpenCL. Just again to mention that CUDA is more tailored for the NVIDIA GPUs. And now we'll look at OpenCL. It might look a little bit cumbersome. It has much more code, especially in the host. But let's dive into the details. So let's first look at the kernel code. It proceeded with the kernel keyword. And then we are using a char. In this case, I'm not manually vectorizing my code. I'm relying on the compiler to vectorize it for me because he knows the architecture, so he can do auto-vectorization. And inside I'm also specifying that it resides in the global memory. If I'm not specifying, then the default one will be the private memory. And inside, I want to understand on which index I should execute my code. So I'm going to use a built-in function that queries the exact index of my thread. So I'm calling getGlobalID in dimension 0. I'm getting my index, and then I'm just adding 5 to this specific index. So just to make sure, imagine that this function is ran multiple times, each time for a different work item. And that's how we are getting the data parallelism. OK, so now let's dive into the host code. It looks a little bit cumbersome, but we'll walk through it. First, you need to define your platform. You may have multiple platforms on your device. Remember that OpenCL was meant to be generic as possible to support as many devices that you can. So you may have several platforms in your chip. And once you have your own platform, then you decide on which device do you want to run your code. And then you define the context, and then you define the queue on which you are going to enqueue your commands. The queue can be in-order queue or out-of-order queue. In this case, I didn't mention, so it's going to be the default, which is an in-order queue. And after that, something special about OpenCL is that the compiler can be just-in-time compilation or ahead-of-time compilation. And your code can reside, and probably will reside, in a different file. In contrary to SYCL and to CUDA, which are single-source compilers, files, in this program, you have to put it in a different file. So you're actually missing here host device optimizations, which is pretty bad for compilers. But in this case, you are able to do just-in-time compilation. You need to load this program. You need to build it and to extract the exact kernel that you want to run. OK, you have your kernel ready. And now you are allocating your device pointer. And then you are performing the write from the host pointer to the device pointer. And next, you are setting the arguments. In this case, I have only one argument in my kernel, so I'm just passing in index 0 the pointer that I'm going to execute on. And then finally, I'm sending and I'm enqueuing the kernel. I'm sending the end range, I'm setting the end range, and I'm going to execute my kernel. And then I'm just reading back the data from, I'm writing back the data from the device pointer to my host pointer, and I'm going to wait on that event. So what you see here, there's a lot of boilerplate code in OpenCL, and actually this is the shorter version because usually in OpenCL they usually use the C API, and there are C++ wrappers that I used here in order to have like a more shorter version of the execution. So this is OpenCL. And the OpenCL standard so that it's a little bit long, and they looked for something smaller and shorter for heterogeneous systems. And that's how we came with SYCL. And SYCL has, for example, at the beginning there's a queue. I'm using a default queue on a default platform, on a default device. I'm having this queue. This is going to be an in-order queue. And then I'm just allocating a device in my memory. And I'm going to copy data from the host pointer to the device pointer. And then I'm going to enqueue, submit a job to my device. So the queue already defines on which device I'm going to execute. And inside this queue, I'm going to have a parallel 4. And this parallel 4 accepts the end range. How many elements do I have? How many work items will I have in each of the work groups? And then I have a lambda function that just does the add, the +5. So in this case, after I finish to enqueue, I'm calling the memcopy. A memcopy to write it back from the device pointer to the host pointer, and I'm going to wait for it. It looks much shorter than what we have in OpenCL. So maybe this language will be more useful and more user-friendly for many programmers. But is it really a C++? It looks like a little bit of C++, but is it really a C++? Well, it's not exactly a C++. You don't have exceptions. You don't have standard C++ libraries. There's no new or delete in SYCL. Function pointers and references cannot be passed between the host and the device. In SYCL, you cannot use them at all. In real time, in heterogeneous systems, usually they are not that efficient anyway. Classes with virtual functions cannot be passed to the kernel. In SYCL, you cannot use virtual functions at all. And kernel functions cannot be recursive. Okay? But those limitations are something that we can live with, because it's not that common in heterogeneous systems where you want things to be in real time. And the next language, I'm just going to show you an example of this language, is OpenMP. And in OpenMP, you can specify that the next block, you want to offload it to your target. You can specify on which target you want to offload it. Or in this case, we offload it to the default target. And then I'm saying that I want to parallel the next 4, and I want to do it in SIMD, meaning that I want to vectorize this loop, and I want to have the number of threads as the number of elements that I'm going to execute in this, as the number of iterations in this loop. So OpenMP looks a little bit more easy going than the other languages. And all of them are just based on C++. So what is a trend? I took this from Google Trends, and see which one is more popular, how many searches were for each of those programming languages. So the first one was OpenMP. OpenMP is pretty stable along the years. It is very popular in the academy. Many people in heterogeneous systems are familiar with OpenMP. And next, there is CUDA. As you can see, it's much more popular than OpenMP. It is used for GPUs. As NVIDIA became more popular, especially after the hype of the machine learning and deep learning, also the CUDA became more and more popular. Next is OpenCL. OpenCL is the answer of the industry to CUDA. And in this case, it started really good, but there is a decline along the years because of the boilerplate code, because it is a little bit cumbersome, I guess. But the answer is SYCL. But SYCL didn't pick up yet. Okay? We wonder if in the future SYCL will be there to pick up. So there is a very nice article made in the University of Stuttgart about the programming languages of the heterogeneous systems, and they summarized it in this graph. So if you are working on an NVIDIA GPUs, in this case, they recommend going for CUDA programming language. If you're not using GPUs, NVIDIA GPUs, then if you are working only on CPU, then it will be probably easier for you to work on OpenMP. Otherwise, you are kind of vendor agnostic, and in this case, if you are looking for performance, you should go for OpenCL. Otherwise, if you're looking for something more user-friendly, then you should try SYCL. Well, it was true about 2 years ago, but SYCL today is much better. The compilers are doing very good work. The compilers were developed by Compute. There's the Compute CPP by CodePlay, and also there are other other companies like Intel that developed the DPC++ as part of one API. It's also a SYCL compiler, which currently is the leading compiler for SYCL. So I think we got much better performance-wise when talking about SYCL. But where does C++? When do we default to C++? That's a question, because we are definitely in a core C++ conference. So what about C++? Well, I'm going to show you an example of a library. If you were in a Ran Gilad lecture, then he showed some of the parallelism available in C++. I'm going to show one example, and then talk about the exciting news that brought by C++ 26 that might help to make order inside this battle of heterogeneous systems. So I'll start with async. Async library. Async, there are many kinds of parallelism. You have unstructured, like thread and mutexes. You have task parallelism, which is async. There's the cooperative, like coroutines. And you also have the data parallelism using the execution library. But let's talk about the async as part of the task parallelism. Let's take, for example, just a simple function, just this add function. I'm adding the value of 5. I'm randomly chose the number 5. And I'm going to pass it as an input. I randomly selected the value of 6. But imagine that this add function will be something much more compute intense, something like a trigonometric function running on a huge array, a three-dimensional array that you want to run as fast as possible. You want to accelerate it. So you want to first to offload it asynchronously to some other device or some other core in this case. So I'm going to use the async function. The async function accepts my function and also the arguments to that function. And it's going to return a future value that I'm going to use. And this future value, I can get it here. And once I return from this function, I know that the execution was done, was finished. So I have the value ready out, and I can just print it. But now, let's do something more complicated. Let's assume that I have another kernel that is running, and I want this kernel to have like an input value that might not be ready when I'm executing my code. So I need some kind of a promise. I need a promise that this value will be ready, and from this promise, I'm getting the future value. And this future value, I'm going to pass it as reference to my kernel. And inside the kernel, I'm going to wait to get this value. So it's going to be stalled until I get this value. When will this value be set? Well, it will be set once the promise is set. The promise is set once I'm calling the set value. And once I'm setting the set value, the execution of the kernel can continue, and it will be done when I'm calling the future get. So I'm having here some kind of a graph. At the beginning, we have the async function, and then the async function execution is told until I have the set value, and then I have the get, and then after I have this get, I finish. I have like kind of a graph here that tries to explain my execution. But the execution can be much, much more complicated than that. Consider a graph of nodes, a deep learning graph that includes many layers. So async doesn't really give me a composition option. It doesn't like then, or doesn't have execution configuration. Like you can't really tell on which resource or GPU you want to execute this asynchronous function. You cannot really do scheduling options like yield and so on. So it is relatively limited. And it's not exactly what we are looking. We're looking for someone to manage all of this. We need someone to conduct this orchestra of devices, to set ahead of time all the work that we want to be done, and then to execute it, to send them, and to set dependencies between them, and parallelize and call a wait function to synchronize between them. So I just want to ask, how many of you ever used or are familiar with the async library before? Just raise your hands. Okay, great. So for all of you that used the async library before, it's going to be very interesting what I'm going to show you now, because that's exactly what C++26 is going to show. It's not yet proved, but it's a proposal that might get into C++26. And for those of you who didn't use async before, then if you are going to work on heterogeneous systems or parallelism, I think you will be very interested in what this library has to offer. I'm talking about P2300. If you were in Robert Leahy lecture, he talked about senders and receivers. I'm not going to talk about extend my talk about all of those features that we have in this library, but just give you a short taste of what we have in senders and receivers. They are part of the standard execution library. So there are three main classes. There's also another class but I'm not going to mention, but the three main classes are the scheduler. You can think of the scheduler as your GPU or your device that you want to execute your code on it. And after the scheduler, we have a sender. All libraries usually talk about senders. So a sender is a work that you want to be executed on your device. And next you have the receivers, which are where the work is terminated, and there are three kinds of channels. There is the value channel, error channel, and the stop channel. So let's look at an example. We have this function. In this case, I'm not really using heterogeneous systems. I'm just using a thread pool. So my scheduler is just a thread pool, but you can think of it as something for heterogeneous systems. NVIDIA already has an implementation for STD execution, which you can use, that execute on their GPU. Okay? So first you need a scheduler on which device you want to execute. I'm going to execute on a static thread pool. And once you have the scheduler, you defined your graph. And how I define the graph, I'm just getting the schedule from the scheduler. I'm telling him that then he needs to perform a function. The lambda function just returns 5. It is really, really simple. And after I'm returning a 5, I'm piping it. I'm sending it next to the next layer, and the next layer is getting this 5, the value, the return value as an input argument, and then I'm adding the value of 7. When exactly this function will be executed? Well, I don't really know. It will be executed asynchronously, but what I do know that after the sync wait, the execution will finish. And when it is finished, I can then ask for the value, for the returned value from this execution, and I can do whatever I want with this value. Okay, so there's a funny thing about standard, but before I'll go over this caricature, I'm going to summarize the talk about the battle of heterogeneous systems. So we have a lot of programming languages out there, and C++ is now coming with a new library that could wrap those programming languages, and hopefully this standard can make some order when talking about heterogeneous systems. There are still some aspects that are not there, like device memory. Vectorization is not exactly a native primitive type that you can use, but it does talk about task parallelism and data parallelism, and it enables you to do a lot of things that you were not able to do before on your code in heterogeneous systems using just C++. Of course, under the hood, those libraries need to be implemented by the vendors of the various system on chips, and then you get your solution. Here is the situation. If you have like 30 competed standards, you somehow want to have just a one type of a standard, which is ridiculous to have 14 standards. So you need to develop one universal standard that covers everyone's use cases. And how do you do that? You have and you create a new universal standard, and then the result will be to have 15 competing standards, which is something very common. So I hope in this case, it's not really what's going to happen. And again, it depends on your heterogeneous system, which programming language suits you best. But hopefully C++ can make some order and to help you choose your accelerator. Okay, so I want to thank you. Again, if you would like to join our meetup group, and join the Israel LLVM meetup. You can join me there as well. You can scan this QR code and join us. You can also contact me through LinkedIn. And yeah, thank you. If you have any questions, go ahead.
So in the proposal that you said is being discussed for C+26, you showed the example of piping one step into another, but are there like more complex ways of building a pipeline? Maybe I want some output to go to 2 separate tasks, or I want to join stuff, etc. So are those also being discussed as part of the step?
Yes. So the standard execution library has several constructs, not just 10, that can help you to parallelize your code to several streams. So you can do it. That's exactly what is part of this library. And I really recommend on seeing what Robert Leahy lecture was about. It talks about all those kinds of constructs, and it's supposed to answer that. Yeah. Sure.
So something like SYCL can really help porting code between different accelerators and different devices, but you still have a lot of work tuning the algorithm and the code for a specific platform. Do you see programming language features or compilers? How can they help with such tasks?
So just going to repeat the question. So SYCL has the option to maybe use a vendor agnostic used as a vendor-agnostic language, and you want to have like a performance comparison. You want to have the best performance on one device and then on another device. So it's a very good question whether we are really able to get the same performance in several devices if you are optimal for all of the devices just by using the same program. And it really depends on the compiler, and it really depends on the device that you have. You don't really always have like performance compatibility between devices, and it changes a lot. It depends on how strange is this device. So some devices can be really, really complicated, and you can't really do something that just like write once and run everywhere and have the same performance capabilities. So, so it really depends on the hardware that you have. Hopefully, SYCL will be able to do that. But as we are creating more and more abstraction and we are getting away from the hardware, then there is a bigger risk to not be optimal for those devices. Okay. So I have to stop now, but please feel free to come over, and thank you again.